Welcome everyone. Today's lesson is entitled Sequences Day 1. This is the introductory lesson to a unit dealing with what are called sequences in series. But really at the end of the day it's all about just an introduction to patterns. Patterns of numbers, how to represent those numbers, looking at a new notation dealing with the representation of those numbers, and just kind of getting used to the idea of patterns. So what I did is I tried to start it out with an investigation into what is called Pascal's Triangle, which happens to be a triangular array of numbers that has a variety of patterns in it. And by the way, we'll happen to see Pascal's Triangle again in the not too distant future and see a context for these numbers and the operations that would produce them. But for right now, it's just all about finding patterns within it and just seeing what we're looking for to kind of set the stage for some of the other stuff. All right, so let's go ahead and begin. So you maybe have seen Pascal's Triangle before, but it kind of starts out just with a 1 on top there. And then 1's always on the outside, so you'll see that in our triangular array. And then the idea is in between every two numbers is the sum of those numbers. So for example, 1 plus 1 gives us the 2. That's the 2 right there. And again, just on the outside, we'll see the 1. And again, starting out with a 1, notice the triangle gets wider as we go down and down there. And as I said, within every two numbers, we put their sum just right below it. So 2 and 1 make 3. So that row right there would be 1, 3, 3, 1. And we'll keep going. I'll just go until I run out of room here. But this would be a 4. This would be 6. Again, just in case you're not catching it, 3 and 3 make the 6. 3 and the 1 make another 4. And then the 1 on the outside. And again, perfect symmetry, as you can see, working left to right here. So this would be a 1, a 5, 10, 10, 5, and 1. And I probably have room for maybe one more row here. So 1, 6, how about a 15 here, 20, 15, 6, and 1. And again, if you want to put a little dot, dot, dot below that, it just keeps going on infinitely, of course. So as mentioned, there are just a few patterns that I figured I would show you in Pascal's Triangle. But let's go ahead and take a peek. So I wrote 3, as you can see here. 2 will kind of work with algebraically a little bit. 1 we'll kind of see tomorrow, which is the Fibonacci sequence. That one's a little more hidden in Pascal's Triangle, but I'll show that to you when I get a chance. All right, let's kind of just start it out here. And by the way, and again, you'll see context for this later on this semester, but when we talk about numbers in a row, actually this row up here is considered row 0. And this is row 1, this is row 2, this is row 3, and row 4, and row 5, etc. And again, this will gel when we start to see context for the operations that we'll be dealing with that match up with Pascal's Triangle. So again, rows and diagonals, by the way. So I just already said row 0, row 1, row 2, etc. And also we would call this diagonal 0, diagonal 1, diagonal 2, diagonal 3, etc., etc. But I don't want to get into that too much. I don't want to get bogged down with that stuff. So sum of the numbers in a row. So row 0, that would be the top one. If I just add up all the numbers, well, of course, I just get 1. Row 1, this one right here. And if I add the numbers in that row, I get 2. If I add the numbers in row 2, so these numbers right here, looks like I get 4. And if I add these numbers right here, this is row 3. And notice it's the one with the 3s matching up with the 1s. So if I add up those, 1, 3, 3, and 1, I get 8. If I add up the numbers in row 4, going across right there, looks like I get 16. And keep going here. Here's row 5. And it looks like if I add up all those numbers, I would get 32. And obviously I could keep going there, but in my table I just stopped at that. And so the idea is, can we write an algebraic expression for row n? So if I gave you any row number, could you tell me what the sum of the numbers would be in that particular row? And again, I don't want to overplay this too much here, but I'm hoping you see that this is these are powers of 2, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth, and of course back 2 to the 0. So it matches up really nicely, not a whole lot of variation needed at all. But essentially the sum of the numbers in any row would be 2 to the n. So you could see right off the bat, if I gave you any row number, 10th row, 100th row, whatever the case may be, you could plug that in right here as an input and come up with the output. And in this case, the output would represent the sum of the numbers in that row. All right? Input, output. Algebraic expression representing the output given any particular input. All right. Very good. Let's move on to the next one. So rather than matching up with a particular row, we'll just call this a term number. So starting with the first input, the second input, the third input, et cetera here. And this is going to be more common to what we're going to see throughout this lesson. So triangular numbers, by the way, happen to be in this diagonal right here. These are what are called the triangular numbers. I'm going to put them in and then I'll kind of explain why they're called triangular numbers momentarily. But if I just keep going with this 1, 3, 6, 10, 15, and we could see what maybe the next one would be. So 1 is the first triangular number. 3 is the next one. 6 is the next one. 10 after that. 15. Now again, I didn't get down to the next one, but you can kind of picture it. It would be right here. 6 and 15 make 21. And you can kind of see it's like here I'm adding 2, then I'm adding 3, then I'm adding 4, then 5, then 6, et cetera, et cetera, et cetera. Now we're going to hold off on this. I'm going to come back to this on the back side of this notes worksheet. So for right now, you don't have to do this if you don't want, but you put a little question mark right there. I'm going to skip it for the time being because it's a little more complicated and come back to it on the, again, back part of this worksheet. But I do want to show you just why they are called triangular numbers. And they are called triangular numbers because I can arrange them as dots and they would form an equilateral triangle. It's kind of cool. So the 1 is not as intuitive, but you can see here's the 3. Notice there's an equilateral triangle. Here's my 6 as an equilateral triangle. And again, the 1, there is my equilateral triangle around that dot. And I could do this with 10, and I could do this with 15 and 21. So I can arrange them as elements inside an equilateral triangle. So they are called the triangular numbers. Just like square numbers, I could do the same thing with squares. Okay, well, I don't want to get caught up in that as well. Again, really just getting used to the idea of a pattern, that's all. Next thing is, this is kind of cool, and we'll see this tomorrow when we look at a different way to algebraically represent patterns. But the Fibonacci sequence, potentially in middle school you did a little work with Fibonacci. Again, don't want to go into the whole history and background of that type of stuff. Just want to kind of show it to you in Pascal's Triangle. It's kind of interesting because it's definitely more hidden. So, by the way, just in terms of what Fibonacci sequence is, it's just adding up the previous 2 numbers to get the next one. So 1 and 1 make the 2, 2 and 1 make 3, 3 and 2 make 5, 5 and 3 make 8, 8 and 5 make 13, 13 and 8 make 21, et cetera, et cetera. You can kind of see that this goes on infinitely. So any number is really just the sum of the previous 2 numbers there. And so, as I said, it's a little harder to see this one. I'm going to do this as light as I can, and I'd encourage you to do the same. It's not on a particular diagonal, but I can draw parallel lines and find Fibonacci's numbers in here. So there's the first one. There's 1. So there's 1. There's the next one. Now, I'm going to try to keep them parallel with this. My artistic abilities are not great, but here's your 2. Okay, there's your 2. So we've got 1, 1, 2. Again, you can kind of just draw nice light line through these numbers if you'd like to just illustrate it. Again, if not, no big deal. But there's our 3. So the 2 and the 1 make the 3. 5 would be the next one. And again, trying to stay parallel with my line drawing there. 1, 3, and 1 make 5. And you can kind of maybe see it at this point. There's my next one. 3, 4, and 1 make 8. And I guess I'll just do the one last one here that I can get to. Here's your 1, 6, 5, and 1, making 13. And I can keep going, and those would be the Fibonacci numbers right there. Again, we'll see this when we write it in a different fashion tomorrow. In fact, I think that's how we start our day 2 lesson with sequences. Okay, so I haven't really done a whole lot except just introduce the idea of patterns. That's all it is. And what we're going to try to do is represent those patterns algebraically. Okay, let's move on. So, a sequence. Let's get a little formal with this. Like most of the things we've been kind of working on here, a sequence really at the end of the day is just a function. So it is a function, though, whose domain is the set of positive integers. So write that in there for me if you would. So one thing to note on this, so like for example, this would represent the domain, the set of positive integers, 1, 2, 3, 4, 5, 6, etc., etc. So that's what we mean by the domain is simply just the set of positive integers. Now what's kind of interesting about the idea of a sequence compared to all the other functions that we've been looking at over the course of the year, we've been looking primarily at what are called continuous functions. Y in terms of x, you'd graph it on the coordinate plane, and you would be able to draw the continuous graph. Okay? Sequences are not continuous functions. They are what are called discrete functions, meaning we're not going to connect the dot and just draw it without picking up my pencil. There's more like one dot and another dot and another dot and another dot. It is what is called a discrete function, not continuous. Okay, and we'll see the graph of one in just a little bit. All right, let's get into the notation for a sequence. So inputs and outputs, because it is a function, of course. So the term number would be representing the input. And as I said, if it's the set of positive integers, it means it starts at 1, 2, 3, 4, etc., all the way up to what we would say the nth term. So unlike all those continuous functions where we kind of did dependent in terms of independent, y in terms of x, the independent variable is not x for sequences. We're going to use n. Okay, and n would represent the term number essentially. All right, now this is going to be some new notation here. So the outputs represent the value at that particular term number. So this, we would say a sub 1. So this would be the value of the first term. A sub 2, the value of the second term. A sub 3, A sub 4, dot, dot, dot. And instead of y equals, we are going to write it as A sub n equals. So this is the value of the nth term, and our job is to write an expression in terms of n. So think of this as your new y. Think of this as your new x, if that makes sense. Okay, now today, we're going to be writing what are called explicit formulas. We're going to be looking at a different type of formula tomorrow, but for right now, what are called explicit formulas. And very simply, an explicit formula describes the nth term of a sequence. And that's pretty much it. It's a function rule is what it is. So formula, and think we just have to be a little careful here. Formula in terms of the input. And again, I'll contrast this with the type of formula we're going to see tomorrow. But the explicit formula is always in terms of n. Okay, good. All right, let's get on to the next piece and just kind of start out with the very basics. So these would be examples of explicit formulas for a sequence of numbers. So again, instead of y equals, it's a sub n equals. And instead of an x as our input, as you can see, it's n as our input. All right, so if I want the first 5 terms of the sequence, what I'm looking for is the value of the first term. So I'm looking for a sub 1. And you can see how the notation fits in. If a sub n is this expression here, and n is 1, that means that n, or in this case 1, will replace the n values right there. So a sub 1 would be in 1 over 1 plus 1. And so without a whole lot of issue, a sub 1 is going to be 1/2. A sub 2, that would be the value of the second term. And so again, don't overthink it too much. You're just putting the input in for the variable and deriving the value. In this case, a sub 2 is 2/3. And I'll go through these now a little faster. A sub 3, okay, is 3/4. A sub 4, 4/5. And lastly, everybody, just first 5 terms. So the value of the 5th term would be a sub 5, and that would be 5 over 5 plus 1. And so you could see this would be 5/6. All right, so the first 5 terms, 1/2, 2/3, 3/4, 4/5, and 5/6. Excellent. Now what I'm going to do is just kind of pause for a second, and I'm going to ask you to grab your calculator. We're going to just take a look at a couple things on here. It's not a major issue. I don't use the calculator a ton through this unit, but I do want you to be aware of 1 or 2 things moving forward. So go ahead and grab the calculator. And what you're actually going to do for me is hit the mode button at the top. And you'll notice a couple things here, but if you go down to the 4th one, we have really primarily just dealt with function mode on your calculator. But if you look on over, there it is, over to the right, you see the SEQ, which stands for sequence. So what we're going to do is actually go ahead and put it in sequence mode. And what's kind of fascinating about it, when you put it in sequence mode and then hit the y equals button, notice in this particular case, you don't get y. They use u instead of a, just FYI. But here it is, in a nutshell, this would be a sub n. Alrighty, and we're just going to do this one here for right now, and maybe we'll revisit this a little tomorrow when we look at a different way to represent these sequences. But what I'm going to do is just take a moment and I'm going to put in my independent variable. And by the way, do you notice this button right here, which we've been using for x, happens to have a whole bunch of other things too, and one of them is n? Well, that is our independent variable. So in sequence mode, the independent variable is n. So it's n divided by, and then n plus 1. Excellent. And what I'm going to do is hit window here just to make sure everything is good. So n, we're going to go from 1 to 10 there. And I think I'll leave this for now. I think the y I'm going to change, just move it up a little bit. We'll see. Just kind of speculating on what we might see here, but I'm going to go ahead and hit graph, and that's fine. Again, if you didn't change it, no worries. But notice one particular thing. As we graph this sequence, notice what I said. It's what is called a discrete function. First of all, it is a function because it passes the vertical line test, but it is not continuous because I'm not playing connect the dot. The domain is not defined in between these positive integers. And so it's what's called a discrete function. One point, and then the next point, and the next point, and so forth, right up the line. And so you could see the values. That would be these guys right here. And by the way, I'm going to go ahead and hit trace. And I encourage you to do the same. And you can kind of see when n is 1, don't worry about the x really, but that's what I'm looking for. There's our 1/2 right there, right? So first term number is 1/2, and if I go to the right, second term number is 2/3, and you could see then 3/4, and et cetera, 4/5, and 5/6. And do you see right up the line, I could keep going and going and going, and so forth. So kind of an interesting little thing to see. We've never worked in sequence mode for sure on the graphing calculator, but you can kind of see the values of these on the screen. 1, 2, 3, 4, 5, all the way up, and you're getting these values right here. All right, let's move on. Okay, you can bypass this a little bit or just be a little quicker, but a sub 1 equals 2 times 3 to the first. And so I get 6. A sub 2 just means the 2 is replacing the n, so it's 2 times 3 squared. And again, not a huge issue, so I should be getting 18 there. A sub 3, and let's see, so a sub 3, 2 times 3 cubed in that particular case. So a sub 3 equals 54. Moving on up here, a sub 4 equals 2 times 3 to the fourth. And should be 162. And lastly, a sub 5, 2 times 3 to the fifth. And I'm getting 486. Again, don't want to overplay it. I know you can plug these numbers in and get them, but essentially we've got a sequence of 6, 18, 54, 162, 486, etc., etc. All right, this is a good one. And what I want you to be aware of here is keeping an eye not just on the values, but the signs of our values here. So a sub 1 equals -1 to the 1 plus 1, and then times 2 over 1. Are you guys getting that as well? Okay, so just putting for a sub 1, that means n is 1, putting them in. And when I get this, -1 squared, because 1 plus 1 is 2, so that's just 1 times 2. So I'm getting a sub 1 equals 2. Excellent. A sub 2 equals -1 to the 2 plus 1, and then 2 over 2, right? Okay, and so a sub 2, now here's a good one. When I do -1 cubed, that would be -1 as opposed to +1 from over here. So -1 times this one, so that should be -1 right there. Cool. A sub 3 would be -1 raised to the 3 plus 1, and then 2 over 3. And so I'm getting a sub 3 equals, and let's take a look. Oh, when I do -1 to the fourth, that just brings me back to +1. So +1 times 2/3 should be 2/3. And I've got a little room here, so I'm going to go down. If you want to keep going across, that's fine. A sub 4, so -1 to the 4 plus 1 over 2 over 4. And so in this particular case, -1 to the fifth is actually -1 times a half. So that's -1/2. And by the way, do you see the signs are alternating? Positive, negative, positive, negative. Cool. I think you could probably see what's happening here and how we'll use this -1 thing in just a little bit. So a sub 5, I've got -1 to the 5 plus 1 and 2 over 5. As long as I know what my particular input is, I replace that number into n and calculate the answer. -1 to the 6th is just 1, so it looks like we get 2/5. All right, very good. So the idea, hopefully after example 1, you're getting a sense of what an explicit formula looks like. These are all examples of explicit formulas. And if I'm looking for particular terms, I could just put that number in for n. So like, for example, if I asked you, what's the 100th term of this sequence, you know to put 100 in for n. So the term number represents the input. Awesome. Okay. Now, let's see if we can take a pattern of numbers and actually write an explicit formula for it. So without too much issue, everybody, let's just go ahead and instead of y equals, remember it's just a sub n equals. So the value of the nth term. Well, what I'm going to ask you to do initially is just below, let's put our inputs. So 1, 2, 3, 4. So we're looking for a rule to match the inputs to those outputs. So whatever I do to 1, I've got to get 3. Whatever I do to 2, I've got to get 7, etc., etc. Now, a couple things to note with this. We're going to keep it relatively simple for now. But I hope you see in the pattern itself, like if I asked you how to get the next number and the next number and the next number, I hope you see that you're just adding 4 each time. So you might want to just put that below here. So plus 4, plus 4, plus 4, etc., etc. And essentially, it's just repeated addition. Well, everybody, you know, we've been doing this since elementary school. Repeated addition is multiplication. So as soon as I see that we are repeatedly adding 4, that means to me that we can use multiplication with our input in order to get the outputs. Now, obviously, 4 times 1 is not 3. 4 times 2 is not 7. 4 times 3 is not 11. So there's probably a little bit more than I need to do here. So I know that 4 times 1 is 4. And then if I subtract 1, that would give me 3. Let's see if that works for the others. 4 times 2 is 8. Subtract the 1, and I get 7. 4 times 3 is 12. Subtract the 1, I get 11. And do you see it works for this one, and it works for this one, and it would for the next one, etc., etc. So repeated addition is multiplication. Notice and think of it as we've seen a constant rate of change. That should sound familiar. Constant rate of change produces a linear expression, mx plus b. And again, we're going to see this type of pattern in a couple lessons down the road. All right. Let's do the next one, a sub n equals. Now, in this particular case, it's the same numbers, except they're alternating negative to positive, negative to positive, negative to positive. So I'm hoping you were paying attention to the last example. I think it was letter C in example 1. How do I get terms to change from positive to negative? Well, what I can do is take the 4n minus 1, because that gives me the numbers, and multiply that by negative 1 raised to, and here's where I have to be careful. And by the way, I neglected one thing. Let's put a 1, 2, 3, 4, 5 as our inputs, kind of matching them up. Now here's the thing. In this particular case, let's put an n plus 1 just for the moment, like the last one, just for a moment. So in the last one, it was like an n plus 1 here. So if you kind of look, if n is 1 to start it out, well, if I start out with 1 right here and then add 1, this becomes negative 1 squared. And negative 1 squared is actually positive 1. And so that would keep me at positive 3 here. So the question is, how do I switch it to negative? And the trick is just take away the plus 1. Because negative 1 to the first is just negative 1. Now I've got negative 1 times that expression that gave me the numbers. And so that should do it. Because then when I do the second one, negative 1 squared, that's positive 1, and so that'll keep me to positive 7 right here. So just be a little careful. As you do some of these problems, they're alternating. Just decide for yourself, should this be an n or an n plus 1, depending on if we're starting out with a positive or a negative value there. Hope that makes sense. Okay, let's do this next one here. Again, matching up inputs and outputs. And let's see what's going on with these guys. And just as I'm thinking about it, let's write a sub n equals. Cool. Now, what's going on in this particular pattern? Well, 1/2, let's see, looks like I'd be multiplying by 2, multiplying by 2, multiplying by 2, multiplying by 2. Excellent. So what I have in this particular pattern is repeated multiplication. Now, I do want us to be a little careful with this. So repeatedly multiplying, repeated multiplication really is just an exponent. So at the end of the day, this should have some variation of a 2 raised to a power here. So I'm just going to start with that for the moment. But my problem, of course, is, 2 to the first is not 1/2. 2 to the first is 2, and that's actually the third term. 2 squared is here, but that's the fourth term. 2 to the third is 8, but that's actually the fifth term. So how do I get this to match up accordingly? And again, I don't want to overstate this too much, but if you see, can I subtract 2 from these inputs? Like 5 minus 2 is 3, then I can raise it to the 2 to the third. 4 minus 2 is 2, then, okay, 2 to the second is 4. 3 minus 2 is 1, okay. So it looks like, again, we'll do variations on this, but if I tweak those inputs by subtracting 2, then apply the base 2 to it, it works out nicely. Okay, super. Let's move on to letter D, and I left this one because I'm hoping those numbers look somewhat familiar. Let's go back a few boards. One more, and there they are. We never actually got a little conclusion on this one. So these are the term numbers, these are the triangular numbers. Let's see. Yep, went one too far. All right, so I'm going to I'll just put it on top this time since I have a little room. So the question is, how do we make inputs produce outputs here? So a sub n equals. And I know you could tell me the next one is 21 because I'm going to add 6, and then I'd add 7, and then I'd add 8, and then I'd add 9. Yeah, that's all well and good. But how can I come up with an explicit formula for that? Meaning if I just gave you n, you could tell it to me. Well, what I'm going to ask you to do is literally just take a moment and just try it. Pause the video. See if you can come up with it. I'm going to give you one hint. It's a combination of inputs producing outputs. So for example, the 1 and the 2 together somehow make this. The 2 and the 3 together somehow make that. The 3 and the 4 together somehow make the 6. The 4 and the 5 together somehow make the 10. And the 5 and the 6 together would somehow make the 15. So pause the video for a minute. Come on back when you want the answer, and I'll give it to you. All right, so let's see how you did. So the way to do this is by pairing inputs and multiplying them together. So 1 times 2 is 2. But if I divide the products by 2, I get this. So 2 times 3 is 6. Divide by 2 gives me 3. 3 times 4 is 12. Divide by 2 gives me 6. 4 times 5 is 20. Divide it by 2 gives me 10. So now that you know that, how can I represent that? This is important in terms of notation. So how would I get a sub n? Well, if you look, to get this, I took the current input, which would be n, times the next input, which would be that number plus 1, and I would divide by 2. And that's it. So if this is the fourth term, the value of the fourth term, I would take the 4 as the input, times 5 as the next input, multiply them, and divide by 2. Now, it just so happens I have a pretty cool proof of this, how to come up with this algebraically. If you'd like to see it at any point, let me know. I just don't want to take our lesson time to do that. But again, if you're interested in seeing an algebraic proof of this explicit formula, just ask, and I'll be happy to go through it with you. Okay, let's get into our last piece. So one of the other operations that will be coming our way, a little bit with sequences, but also kind of down the road a little bit, are what are called factorials. So the symbol with a factorial is an exclamation point, as you see here. And a little definition for us, just to get us going. I'm just kind of looking at the time. I want to make sure that I get everything in relatively fast. So by definition, everybody, 0 factorial is going to be 1. And in fact, I gave you a little table over here. So 0 factorial is 1. And here's how we're going to process this, essentially. So n factorial, so any number factorial, again, that's the exclamation point, is really that number times all of the positive integers before it. So we would kind of write this as the nth term times the n minus 1th term times n minus 2 times n minus 3, all the way down to the last positive integer, which would be 1. So this works for all positive integers. In fact, I want you to write that. So this is how we're going to define it in a very discrete fashion, only for positive integers. And look at the table that I just gave you off to the side. Again, 0 factorial is defined separately as 1. But then for all positive integers, this is how it is defined. So I'm just going to give you a for example, just in case you've never seen this before and you're still not 100% convinced. So what this means, like if I gave you 7 factorial, all that means, everybody, is I start with 7, and I'm going to multiply it by all the positive integers below it, all the way down to 1. And so if I did take 7 times 6 times 5 times 4 times 3 times 2 times 1, I would actually get 5,040. Now the reason I gave you this table, I was going to do a little more with this, but again, just in terms of the time, I don't think I'll be able to, is just to show you how incredibly fast factorial growth is. You know, we talk a lot about exponential growth and how fast exponential growth is, but nothing compares to factorial growth. So look how quickly these factorials increase. It goes from 1 digit to 2 digits quickly, then 3 digits, then 4, then 5, then 6. And you can see how incredibly fast. Just 10 factorial. Pretty harmless, right? 10 times 9 times 8 times 7 all the way down to 1 is over 3.5 million. And you can see how incredibly huge these numbers get. Look how big just 20 factorial is. Look how big 25 factorial is. I mean, just, it's astounding. So again, I could do some more stuff with this. In fact, I was going to show you a little pattern with 0 factorial, sort of show how that kind of fits into the mix as well. But again, I'm kind of looking at the time here, and I just don't want to use that for our purposes. So let's do example 3. Again, just now an explicit formula. I could come up with any term. In this case, I'm asking for the first 4 and the 10th. So a sub 1 equals, and then a sub 2 equals, a sub 3, a sub 4, and then all the way to a sub 10. Okay, let's just get these quickly. And I'm going to show you on the calculator also the factorial just as we go through this. You could certainly use the table that I gave you right here for a little bit, but again, I want to be quick and then show you on the calculator to wrap this on up. So a sub 1 is literally just 1 factorial over 1 squared. 1 factorial is 1, 1 squared is 1, 1 over 1 is 1. A sub 2, 2 factorial over 2 squared. And so again, here we go. 2 factorial is 2. 2 squared is 4. So it should just be 1/2. 3 factorial over 3 squared. And starts to build up a little bit here. So 3 factorial, as you can see, where is it? Is 6. 3 squared is 9, so 6 over 9 equals, call it 2/3. A sub 4, so 4 factorial over 4 squared. And I look in my table there. 4 factorial is 24, and 4 squared is 16, so 24 over 16, and reduce that to 1 1/2. 3/2 would be fine, something like that. And lastly, let's do this one on the calculator just so you know where this button is, because again, we will be using the factorial calculation. So 10 factorial over 10 squared, even though it's in the table, let's do it here. So everybody, go to your calculator if you would. I'm going to go to my main screen, and I'm going to hit 10. I'm going to go to Math. So everybody hit the Math button. And you're going to move it 1 to the left to get over to PRB. And by the way, this context is where we're going to see factorials come out. And Pascal's Triangle is going to come out again with this NCR. But anyway, number 4. Do you see the exclamation point? So number 4. So 10 factorial divided by 10 squared. Oop. Try that one more time. There we go. And I get 36,288. Could I come up with any particular value in this sequence if I know the input? Absolutely. So that's the idea with an explicit formula. If you know the input, plug it in, come up with the output. All right, everybody, I'll stop right on there. Feel free to ask questions on the triangular numbers if you'd like. And if you want to look a little more at that 0 factorial, I can show you a quick little pattern with that too. Thanks, everybody.